Well, let's get started with review for exam 4 in chapter 6, thermochemistry. And the first highlighted one I've got is this one, number 2. What is the kinetic energy of 1.56 kilogram object? 1.56 kilogram is the mass of the object. Moving at 94 kilometers per hour. 94 kilometers per hour. The units are in, the answer units are in kilojoules. So in order to make the calculation come out right at joules, kinetic energy equals 1/2 mass times velocity squared. These have to be in SI units, fundamental units. So this one's going to be in kilograms, which is good. It's already in kilograms. The velocity has to be in meters per second. So we got to change this one to meters per second. Do a little dimensional analysis here. All right. Remember, whenever you have units that you're going to convert and there are more than one unit in the original, do one at a time. So I'm going to do meters first. Kilometers we want to cancel and leave us with meters. That's this part. So we have 1,000 meters in a kilometer. Right? That cancels kilometers. Now we can do hours. So how many seconds in an hour? If you don't know, yep.
60 seconds.
Yeah, keep going. Yeah, so that would be. If you can't remember,
I can't put it in my brain.
just do this. Right? We're going to cancel hours and make minutes because we know what the conversion is, 60 minutes per hour. Then we're going to convert minutes into seconds. Oops, sorry. Minutes on top. And seconds on the bottom. So it's 60 seconds per minute. So that'd be 3,600 seconds per hour. Okay, then where's my calculator? So we've got 94, and when you've got a chain conversion like this, just multiply across the top and then divide across the bottom. So I'm going to say 94 times 1,000. And that's it. Then divided by 60 and divided by 60. So that's 26.1. I'm going to keep an extra one just to avoid rounding error. That's in meters per second. Minutes cancel. So we've got seconds here, we've got meters here left over. Now we can plug them into the formula. Kinetic energy equals 1/2 times mass, which is 1.56 kilograms, times 26.11 meters per second, and that's squared. And the units of energy with these fundamental SI units, the unit for kinetic energy is going to be joules. So I already got 26.11 in there. I'm going to square it. And then times 1.56. And then divided by 2. So that gives me 5.32 times 10 to the second joules. The answer is in kilojoules. And so, did I do that right? Let me check that again. 26.11. Let me see if I did this one right. 94. I want to do that again. So it didn't work. Let's try it again. 94,000 divided by 60. Yep, 26.1. Okay, then I'm going to square that because that's the velocity. And 1.56 times that and then divided by 2. Yeah, that's right. Okay. So we have two options. We can try to figure it out. If this is joules, in kilojoules, remember that as the unit gets bigger, the number gets smaller. So if the number gets bigger by 1,000, it's going to take away these two plus another one from here. 0.532 kilojoules. Oops, I went the wrong direction. Can you listen to myself talk? All right. Yeah, I had it right. 0.532 kilojoules. But our answer is in scientific notation. So it needs 5.32 times 10 to the minus 1 kilojoules. There you go. All right. Okay, number 3. Which of the following statements correctly describes the signs of Q and W for the following exothermic process at 1 atmosphere and 370 K? All right, process is H2O gas going to H2O liquid. Did I get that right?
Mhm.
Yeah. So that's definitely exothermic. If you're going from gas to liquid, this has a whole lot more energy in it than that. So when it goes to liquid, it's got to give up that energy. So the delta H is going to be negative. All right. And if the pressure is constant, which we're told it is, pressure is at 1 atmosphere, it's constant. That means delta H and Q are the same magnitude. And of course, the same sign. And the temperature is 370. We may need that and we may not. All right, so exothermic process, Q and W. So Q is going to be negative, right? We already termed that from exothermic reaction. And how about W? All right, so drawing a picture helps here. If you got this cylinder, right, with a frictionless piston in it, and there's 1 atmosphere pressure on the top, and this water gas in here first. So what happens when that gas condenses? It's not pushing back against the piston anymore, is it? Well, not much. So it's going to contract, right? So if this is our system, it's the volume is decreasing. And let me see, let me be sure I've got this in the useful information. Let's see, here it is. That's P times delta V. W equals minus P times delta V. So if the volume is decreasing on this system, that means the volume afterwards is smaller than the volume before. And volume final minus volume initial. This is going to be larger than that one. This makes this one negative. Pressure is constant, so this is going to be a positive value. What that's saying is, as this decreases, work is being done on the system. That means this is positive. Okay, so C should be the correct answer. An expanding gas does work on its surroundings. A contracting gas, if you need to think of it those terms, that's a good way to do it. A contracting gas works on the system. Expanding gas works on its surroundings. Like a gasoline engine, right? When does it produce power? When the volume is increasing, when the cylinder is being forced down. It's doing work on its surroundings. And that's how you get from point A to point B in your automobile. All right. Who's next? Skip a few and go down to 7. 1 mole of an ideal gas is expanded from a volume of 1 liter to a volume of 8.93 liters against a constant external pressure of 1 atmosphere. Okay. How much work in joules is performed on the surroundings? Right. It already tells us. And the work is in joules. So first we have to do the calculation of work. Right. We just had it up here a minute ago. Pressure times change in volume. So the pressure is 1 atmosphere, correct? Yes. So we got 1 atmosphere pressure, and we got a change in volume. What's the final volume? 8.93 liters. Minus an initial volume of 1 liter, correct? Okay, so that would be, this is going to be a positive. This is a negative. So it's going to be a negative value of minus 1, 7.93 liter atmospheres. But those are not our units. We got to convert. 1 atmosphere, 1 liter atmosphere is 101.3 joules. So now we got to convert this units. Liter atmospheres on the bottom, joules on the top. And the ratio is given right there. 1 liter atmosphere is 101.3 joules. So we multiply 101.3 times 7.93. And I get 803 joules. Is it in joules? Yeah, the answer is in joules. That's negative. We still got the negative. And that comports with expanding gas does work on its surroundings, which should be negative relative to the system. Okay. And about number 12. Calculate the work associated with the compression of a gas from, oops, got it. Michaela's company. Where Patricia is. Haven't seen her. Oh, there's a chat. Let me see what the chat's about. Oh, okay. It happens. Desiree lost service and she came back. Okay. The work associated with the compression of a gas from 121 liters to 80 liters. So we're going from the change in volume is equal to final, which is 80 liters, minus initial, which is 121 liters. Okay, so that's our compression gas. Yeah. So we're actually doing work on the system. That's a minus 41 liters, change in volume. Okay, at a constant pressure of 13.1 atmospheres. So pressure is held constant at 13.1 atmospheres. So we can calculate work as minus P delta V, which is equal to minus pressure and change in volume minus 41 liters. Okay, so 13.1, 41 times, and this negative, and that negative make it a positive. At 537 liter atmospheres. And what are our units? Liter atmospheres. So it's a positive 537 B. The sign convention here is important. If for no other reason, the fact that you've got A and B with the same magnitude and different signs. So you got a 50-50 chance if you don't know the sign. Let's see. Okay. That means work is being done on the system. Okay, we've got a series here, 14 to 17 is based upon this first statement. 14, 15, 16, 17. All right. A gas in a 1 liter bulb at standard temperature and pressure is connected via valve to another that is initially evacuated. So we've got a 1 liter bulb here. And it's connected through a valve to another. And it doesn't say what the other one is. It can be any size we want. This is a vacuum. And this is a 1 liter bulb at, let's see, 1 liter bulb, standard temperature and pressure. So it's 1 atmosphere and 25 degrees C, or whatever K that is. All right, answer the following questions. What's true about each one of these values? Positive, negative, equal to 0, less than 0, greater than 0. That's the same for each one. So the first one is for Q. The second one is for W. 16 is for internal energy. And the last one is delta H. Okay. We can take these in any order you want, actually. How about W? Let's take W first. Is any work being done? Well, in order to do work, we have to exert a force through a distance, right? So a distance is there, but there's no force because there's no resistance from that vacuum, right? So work equaling force times distance, that's okay, but that's not there. So this is equal to 0. There's no work being done. Okay. How about Q? Well, Q, we're told that this whole process takes place at standard temperature and pressure. If the temperature is not changing, then Q is also equal to 0 because we measure heat based upon difference in temperature. Since there's no difference in temperature before and after, then Q is 0 also.
You said it's because temperature's not changing, it's staying the same.
Yeah, it says, let's see, consider a gas, standard temperature and pressure connected to a bulb. When you open the two bulbs, the temperature remains constant. So if delta E is equal to Q plus W and both of them are 0, then it has to be 0 too. And this one's a little difficult to rationalize because if this is under 1 atmosphere pressure and it's expanding into a vacuum, the pressure is not going to be 1 atmosphere anymore. All right, so saying this one is equal to 0 because Q is equal to 0 is that line of reasoning doesn't seem to hold. But we also don't have any change in temperature. Right, and that's required for either the actual heat transfer or the enthalpy, which is potential. Right, so we sort of have to stretch our minds a little bit for that one. But the long and the short is, under these conditions, all of those values is 0. How about 18? Of energy, work, enthalpy, and heat, how many are state functions? I think I left the, yeah. I left the ones that are state functions highlighted or bolded. Right? So if we're looking at energy, enthalpy, heat, and work, those, yeah, heat. Yeah, they're all there. Right. These are state functions. All you need to know is the current state, how it got, and what it started at, beginning and end. You don't care about in between. These are both path functions. You need to know the pathway that they took to calculate those. All right. Number 19. Which of the following properties are intensive properties? That is, they don't depend on the amount of something. Right, so what do we have? In 5. Last one is energy.
Yes.
Then we have concentration. I'm working my way up. Volume, temperature,
Next.
and mass. Okay, so which are intensive properties? Mass depends on how much stuff you have, right? So this is extensive. Temperature is going to be the same no matter how big the object. If you measure a temperature in this and a temperature in me at the same value, doesn't matter. So this is an intensive property. Volume depends on how much there is. Concentration is an intensive property due to the fact that it's ratio of 2 extensive properties. Whenever you get a ratio, you can bet that it's going to be intensive. And energy depends on how much there is. So we've only got Roman numeral 2 and 4 are intensive properties. That's C. All right. 23. Okay. Consider this reaction, the following proposition. The reaction is endothermic, exothermic. Enthalpy term would be different if the water form was gaseous. Which of the propositions is true? Okay, let me put the whole thing up here. I think we got time. This is ethanol. It's the drinking kind. 3 oxygen gas. And it's going to make carbon dioxide and water. And in this case, the water is liquid. Delta H is a negative 1.37 times 10 to the 3rd kilojoules. Okay. So first, is the reaction endothermic? First one is endothermic. Is that true? Nope. because delta H is negative. Right? Everything's in reference to the system. If it's negative, that means heat's leaving the system. So this is actually exothermic. That was the easy one. The third one takes a little thought. The enthalpy term would be different if the water formed was gas. Gas instead of liquid. Remember when we went from liquid to gas, it had to give up energy. I mean, when we go gas to liquid, it had to give up energy. So in order to go from gas to liquid, there's some of that in there is a phase change. So if it were gas, this value would be less negative, maybe 1.2 or something like that. Yeah, so that does make a difference, right? Phase change makes a difference in the enthalpy. Simply because it does either take energy to vaporize a liquid or get energy back from condensing a liquid. So 2 and 3 are correct. That's E. Okay. Next. '24. Let me see where I made that. You might be able to go a little further that way. Next Tuesday, we'll have time to do a little pre-lab thing. We haven't done any pre-labs on this one yet, have we? Okay. All right. So if I can go a little farther today, then that'll give us time on Tuesday. How much heat is required to raise the temperature of 5.75 grams of iron with a specific heat of 0.45 joules per gram degree centigrade from 25 to 79.8? This is a calorimetry problem. So let's put what we know up here. The mass of the metal is 5.75 grams. Okay. Its specific heat we're given is 0.45. That's in joules per gram degree C. And let's see. Initial temperature is going from 25 degrees C to final temperature of 79.8 degrees C. Okay. Now we know what the formula is. Q, the heat change here is due to specific heat times the mass times the change in temperature. So we've got the mass here. Well, let's put them in order. 0.450. I'm going to leave the units out because just to save space. 5.75. What you need to do first is determine, are the units correct? Like, this isn't kilograms, it's grams. That's good. Degree C, that's good. And it leaves you with joules. And then the change in temperature is final minus initial. 79.8 minus 25.0. I said I was going to leave the units out. Okay. So that's the thinking part. The rest is number crunching. 79.8 and 25 times 5.75 and then times 0.45. So I get 142 joules. Okay, and that's a positive. Right? Positive. That difference is going to be positive. That means, and they said, how much energy does it take to make the metal go from 25 to 79? We're putting energy into the system. So it should be positive. We're adding heat to the system. And that's E. E is the answer. Right. .26.
All right. Let me read that one. I got stuff in my way here. Let's see, is there anything? No, it's okay. A 32.5 gram piece of aluminum with a molar heat capacity of 24.03 joules per degree mole is heated to 82.4 degrees and dropped into a calorimeter containing water, specific heat of the water, initially at 22.3. The final temperature of the water is 24.2. Calculate the mass of water in the calorimeter. All right. So let's put what we know up here first. The mass of the aluminum is 32.5 grams. The mass of the water is our unknown. Okay. The specific heat of the aluminum, and this is molar specific heat, 24.03 joules per mole degree C. And then the specific heat of water is given in grams, which is 4.18. I think some will put 4.184, but we'll use their number so it'll give us closer to the answers that are available. Joules per gram degree C. Okay, temperature. Initial temperature of the aluminum is what? 82.4 degrees. Okay, the initial temperature of the water is 22.4, 22.3, 22.3 degrees. Okay, what's the final temperature? Final temperature is 24.2. What's the final temperature of the metal? Of the aluminum? It's the same as the water. Why? Because they're at equilibrium now. They have to be the same temperature. Okay, so we've got everything I think we need, except for the calorimeter, and we're assuming that it contributes nothing. This is a theoretical operation. Okay, remember? Everything that happens in Vegas stays in Vegas. So we've got the heat change for the aluminum and the heat change for the water. Account for all the heat changes that occur inside that calorimeter. Now we can parse it out. So this Q of aluminum is the S of aluminum times the mass of aluminum times the change in temperature for aluminum. Okay. And then we add that, the specific heat for water times the mass of the water, which is our unknown, and change in temperature for water. Okay. I'm going to run out of board space here. All right, so the specific heat for aluminum is 24.03 joules per mole degree C. All right, there's our first hiccup. We can't use mass of aluminum. We have to use moles of aluminum to cancel that number. So we got to take this grams and convert it to moles of aluminum. Right? So aluminum is 2698 grams per mole. Take 32.5 and divide it by 26.98. And that's 1.205 moles. Now we can put that in here. 1.205 moles of aluminum. And then the temperature change is going to be final minus initial, 24.2
minus 82.4. Okay, that's the aluminum, what it's doing. Now we need the water. Right, 4.18. I'm gonna have to leave the units off to squeeze it in here. Grams of water, that's unknown. Mass of the water. And then the change in temperature for the water, which is final 24.2 minus 22.3. Right, there it is. Okay. Now, all of these are numbers, so we can combine these into a value. Let's see, I've already got this one in my calculator, so I'm gonna multiply it times that one. And then I'm gonna subtract these two. 24.2 and minus 82.4 times. So this one is going to be minus 168.5. Joules. Moles cancel, degrees C cancel, leaves us with joules. And this value is going to be 24.2. Yep, minus 22.3 times 4.18. That is 7.942 times the mass of the water. And that's all equal to 0. I think I did that right. Yeah, that looks right. And this is about 2 times 4 would be 8. That's close to 8. Okay, so now we need to put this one on this side, or it'd be easier. If we put this one on this side, it becomes positive. And then we flip the equation around. So 7.942 times the mass of the water is equal to 1685. All right, this 7.942, let's see, we multiplied degree C. So the only thing left here in units is the only thing left there, since we multiplied temperature times that, is joules per gram. This is joule per gram is the units for that one. Times the mass of water, which is grams, will leave us with joules. Okay, so now to solve for this one, we just need to divide this one, 85 joules per 7.942 joules per gram, and the joules cancel and the grams, right? The denominator is the numerator. So that flips up top. And let's see. 1685. Switch those and divide. 212 grams of water. Okay. Did I lose you? Just can't see around.
Yeah. I got it.
Okay. So everything revolves around this equation. The hard part was figuring out what goes where. That's why I wrote it all out here. So that you could see where it goes. And with this minor change, well, actually a major change, it's moles rather than mass because of this value. Joules per mole degree C. We can't use mass of aluminum, we have to use moles. And then the rest of it was solving for the unknown. That was 26. Hey.
627. 45.9 gram sample of a metal is heated to 95.2, placed in a calorimeter containing 120 grams of water at 21.6 degrees. The final temperature of the water is 24.5. Which metal was used? All right. So let's say we've got water and metal. So the mass of the metal is equal to 45.9. 45.9 grams. And the mass of the water is equal to 120 grams. Okay. Let's see. The specific heat of the water is equal to 4.18 joules per gram degree C. And the specific heat of the metal is unknown. That's what we're going to use to determine which metal it is. Let's see, initial temperature of the metal equals 95.2 degrees C. And the initial temperature of the water is initial temperature of the water is 21.6. Final temperature of the water is 24.5. And the final temperature of the metal is exactly the same. Okay, I think we got everything we need now. All right, we have the Q of the metal plus the Q of the water. And then the Q of the metal is the specific heat of the metal times the mass of the metal. Excuse me. Yeah, mass of the metal. And then the change in temperature. And then the specific heat of water times the mass of the water times the change in temperature of water. There we go. Well, now we just parse it out. Like the first one, this is unknown. The mass of the metal is 45.9 grams. Okay, change in temperature is going to be final minus initial. Okay. And then for the, we'll come down here so it don't run off the edge. Water is 4.18 joules per gram degree C. Times the mass. Like this. The mass of the water is 120 grams. And then change in temperature is final minus initial. Here we go. So let's see, this one is going to be reduced to a value times an unknown, 24.5, and then 95.2 minus that, times 45.9. So this is minus 3,245 times the specific heat of the metal. And this one's going to give us a number. 4.18, 120, and 24.5 minus 21.6 times all of that. Oops, messed up. Let's try it again. Punch the wrong button. There we go. Well, this is 1455. Okay, so if we move this one to the other side, it becomes positive. Equals to this one. This one then becomes, it looks too much like mass, metal. 1455 divided by 324
And this is gonna be joules per gram degree C. Let's see. And I get minus, no, I get the value of 0.448 joules per gram C.
So best candidate, iron. Closest one. Notice that when we put this chunk of iron in there, it goes from 95 to 24, but the water only goes up from 21 to 24. Which means that the specific heat capacity water is much greater than it is for iron. In other words, water can absorb more heat for each degree change than iron can. Okay, 28 coming up. All right, you take 295.5 grams of a solid at 30 degrees and let it melt in 425 grams of water. The water temperature decreases from 85.1 to 30. Calculate the heat of fusion of this solid. Okay, we didn't talk about heat of fusion. Heat of fusion, which is, we usually give it the enthalpy term. Heat of fusion. F means formation, so let's make it explicit. Heat of fusion is equal to the amount of heat required for a phase change from solid to liquid per gram. So it takes that much heat per gram to go from solid to liquid. We add that much heat, or if we go from liquid to solid, it gives up that much heat. Right? Okay, so we're starting off with 295.5 grams of the solid. So the mass of the solid, let's do it this way. The mass of the solid is equal to 295.5 grams. The mass of the water equals 425 grams. Okay. Let's see. The solid is at 30 degrees. Okay. The initial temperature of the water is 85.1. 1 degrees C, and the final temperature is equal to 30 degrees. That's important because there's only one temperature for a heat of fusion. Temperature, when we're calculating the temperature of the heat of fusion, the temperature of the substance cannot change from solid to liquid or liquid to solid. If it changes from, if it's heats or cools down in either one of those phases, then we're talking about specific heat calculation. We only want this simple temperature at 30 degrees. Okay. So we could look at this as, yeah, we could do, right? This is equal to the heat of fusion plus the heat for the water. Right? So the heat of fusion is going to be this value times its mass. Right? So this value, rather than SM delta T, it's just going to be the heat of fusion And we can tell that from the units of measure. Dimensional analysis will tell us what needs to be here. So this heat of fusion, which is in joules per gram, times the mass, 295.5 grams, will give us a joules value because this gram cancels that gram. And then the heat over here from the water is the S and delta T. So S for water is 4.18 and mass is 425 grams. And then the delta T is final minus initial 85.1. There you go. Okay, so this is still 295.5 times the delta H. And this is going to be a value. Right, those two together, and then the difference here. There we go. So I get this value right here is minus 9,789. Oops, that was further than that. 5 joules. Okay. So if we put that negative on this side, it becomes positive 97885. That's 97,885 joules equals 295.5 times delta H. Delta H, the fusion is 97,885 divided by 295. Which is 331. 331 joules per gram. Let's see, does it joules? Yes, joules. C, 331 joules. The other way you can approach this is the way that Professor Dave explained it. How much heat is being delivered by the water? You calculate that from here. How much heat? That heat is the same amount of heat that's used to melt the substance. Right? So if you divide that much heat by this many grams, you get the joules per gram, and that's your value. Either way works. It's just with this, I keep it in a nice, neat package. And we use the same approach for every problem. 0 equals. For a calorimeter, that's always the case. 0 equals something. 28 is history. Okay, 28. 32. We still got a few more minutes. And we can get a jump on next time we do. 32. In the lab, you mix 2 solutions, each originally at the same temperature. The temperature of the resulting solution decreases. Which of the following is true? Well, if the temperature decreases, right, temperature decreases when we do that, that means we're dealing with an endothermic reaction. That's obvious. Temperature decreases. Chemical reaction is releasing energy. No. Right. A is false. How about B? B, the energy released is equal to S times M times delta T. No, we're not. Because we didn't put . that by itself will not tell us, will not give us the answer because we've got two solutions. Bring them together. We need both of them. So if it had said SM delta T for one versus the SM delta T for the other one, but actually in a chemical reaction, you're dealing with the enthalpy for that reaction. So to calculate the enthalpy for the reactions, you need to invoke stoichiometry, not calorimetry. Chemical reaction is absorbing energy. That's true. This is the same thing. It absorbs energy. Chemical reaction is exothermic. No, more than one of these. Oh. Now, I was just looking back at B. We still can't use just SM delta T to answer the question because we don't know the mass. We don't know the moles going into it. We don't know anything about the temperature, right? So B by itself won't answer the question. That's why C is only the best answer. Let's put it that way. It's the best answer. 36. Let me see. Exactly 123.7 joules will raise the temperature of 10 grams of metal from 25 to 60 degrees. What is the specific heat of this metal? Oh, this is an easier one than one before. 123.7 joules. 7 joules will raise the temperature of 10 grams of metal from 25 to 60 degrees. So just to keep it positive, I'm doing it backwards. So that's a simple calculation. This is the way that you calculate S. 123.7 divided by 10, and then 60 minus 25. Add that into it. We get 0.353 joules per gram degree C. This is degree C, this is gram, this is joules. So the units are correct for S of the metal. And that would be B. That's the specific heat for this metal. And that's 38. On a cold winter day, a steel metal fence post feels colder than a wooden fence post of identical size. Because, all right, if it feels colder, right, let's see, there's the wooden post and there's the metal post. If the metal feels colder, then the temperature change, T, must be greater than the temperature change for the wood, right? If it feels colder, the temperature has to change more for the metal. That's our starting premise. So why is that? Well, let's see. I'll look at the answers. A and B talk about specific heat capacity. Steel has the ability to resist temperature better than wood. The mass of the steel is less than the wood, so it loses heat faster. All right, there's no mention of mass of either one. So we have to focus on the specific heat capacity. If the temperature, so what we'll be looking at here is the heat transfer for this wood would be S for the wood times the mass of the wood and times the delta T for the wood. In this one, the heat change would be the S for the metal times the mass of the metal and times delta T for the metal. So what's constant and what's variable?
Well, this is gonna be different. These two are gonna be different. We've already said that. This one's gonna be greater than that one.
So why don't we solve for those?
Solve for this delta T, wood. This is metal. So let's solve for this one. Delta T for the wood is equal to Q divided by S for the wood times the mass of the wood. And this delta T is going to be equal to Q times the S of the metal times the mass. All right. Well, we know that the specific heats are going to be different. So we can ignore those for now and use those later. So the mass of the wood and the mass of the metal, we have to make an assumption here that the mass that's being exposed to your tongue, right? Is it your tongue or you just feel it feels colder? Okay, so we're not sticking our tongue to the metal post. Right, let's say we just grab it. So the amount of mass that's available to your hand, we have to say it's roughly equal. All right, so if this is constant with this one, how about the heat? The heat transfer. Well, in order for the change in temperature to be greater for this side than that side, then something over here has to be different. Now, if we allow the Q to also be different, then we have to look at this ratio. If this Q is different than this Q, then it's the ratio that's important. So if this is greater than that one, then this ratio, that means this has to be greater than that relative to this one greater than that. But if the Q is constant for both sides, then all we have to focus on is the specific heat. And for this one to be greater, that means this one has to be smaller because it's in the denominator. So if this one is smaller than that, that means the calculation here would be larger.
Let's see if that fits at any of our choices. The specific heat of the steel is lower than the specific heat of the capacity of the wood is B. That would be an acceptable answer with the assumption that
These are the same and these are the same.
that's the only way you can resolve it, because steel has the ability to resist temperature change better than wood. Is another way of saying that steel has a higher heat capacity than wood, and we know that's not true. And there's nothing said about the mass. So this is kind of you have to choose. You have to make assumptions and choose. And I choose to say the mass is the same and the Q's are the same. That allows me to focus in on the specific heats. Right? That's not a really good question though, is it? That's the one that separates the sheep from the goats.
All right, let's see. Got room for one more, maybe? It's not too long.
43. 43. Consider this reaction. Okay, that's the one we were looking at earlier. All right. We're going to combust ethanol. When 21.1 grams of ethyl alcohol with that molar mass is burned, how much energy is released? All right, let's do this one.
So you need your equation, you need your balanced equation. That's absolutely essential. Three, yeah, three. And then 2 carbon dioxide plus 3 water. And the delta H is equal to minus 1.37 times 10 to the third kilojoules. And remember what I said earlier, that delta H, if it doesn't have a denominator, kilojoules per what, then it's for this reaction as written. It's that many kilojoules for 1 mole of this.
or that many kilojoules per 3 moles of that, or per 2 moles of that, or per 3 moles of that. So what are we given? We're actually given 21.1 grams of this. So it's that value per mole of ethanol. But we need to know how many moles of ethanol we have. So we got to convert this to moles. All right, grams on the bottom to cancel and leave us with moles. And we're given the molar mass here at 46.07. So we got 21.1 and 46.07 divided. And that gives us with 0.4580, rounded off. Moles. Ethanol. That's my abbreviation for ethanol. Now we need to calculate the amount of energy. If that's per mole, if it's let's see, and our answer is in kilojoules. That's good. 0.4580 moles of ethanol. And we have this many kilojoules per mole of ethanol. And that cancels the moles and leaves us with kilojoules. 1.37, change that sign to the third power. And then multiply. So this gives us minus 6.27 times 10 to the second kilojoules. Nope, it's in standard note. Oh, there it is. Yeah, it's in scientific notation. C, 6.27. Now, the key here is that there are no negatives there. And the reason it is because the problem says how much energy is released. When it says released, this has to be negative. So the answer is just the absolute value, 6.27 times 10 to the 2, 10 squared kilojoules. Oh, I got 5 more minutes. Anytime I can use up now is less time we have to spend on it next Tuesday. So let's try to get one more under our belt. Is this using the same equation? No, good. Otherwise, I just erased them. So we've got H2 gas plus 1/2 oxygen. That's yields H2O. Delta H equals minus 286 kilojoules. All right, what does that look like to you? This is the heat of formation. And all right, this is the heat of, this is not strictly speaking the heat, this is not the standard heat of formation because we don't have a 0 there. But this is the heat of formation under the conditions given. Right, at 24.7 degrees and 1 atmosphere. So the pressure is standard, but the temperature is not. How much energy was evolved when the Hindenburg burned? As 2.11 times 10 to the 8th liters of hydrogen. 2.11 times 10 to the 8th liters of hydrogen gas at a pressure of 1 atmosphere and a temperature of 24.7 degrees. 7 degrees C. All right. Remember, if we want to figure out how much of this is related to how much of this has to be in moles. Right? Because all delta H's are referenced to moles of something. So we got to find out how many moles that is. Well, we've got volume, we got pressure, we got temperature.
we can calculate moles. RT over PV. This is gonna be plus 273. So the number of moles then is gonna be 0.08206 liter atmospheres per mole K times temperature, which is, let's see, 0.779, 298K, 297.7K. Pressure is 1 atmosphere times the volume of 2.11 times 10 to the 8th liters. And the volume is correct because our unit of measure here is liters. This is atmospheres. So it's going to leave us with moles. Let's see. Did I do that right? No, I didn't. I've got it upside down. Nobody was going to catch me on it either. The reason I questioned it was because if my answer is going to be in moles, why is moles in the denominator? Okay, that was the clue. That I had it upside down. All right. So we need to switch these around. This is 1 atmosphere on top. And 2.11 times 10 to the 8th liters on top. There we go. Now on the bottom, we have 0.08206 liter atmospheres per mole. That's better. And then I got to do it again. 297.7. Okay. There we go. So this gives us the number of moles of gas. 1 exponent 8 and 0.08206 divide and 297.75. So this is 8.637 times 10 to the 6th moles of hydrogen gas. Now, that much heat per mole of hydrogen. So if this is the number of moles, then all we need is minus 286 kilojoules per mole of hydrogen. So 286. And I get, well, let me put it out here. Minus 2.47 times 10 to the 9th kilojoules. Is that one of our answers? Well, how much energy is involved? So they're assuming it's negative. All right, D, 2.47 times 10 to the 9th kilojoules. So one of the subtexts of this lesson, this problem is pay attention to your units to catch mistakes.
Can you times the 8.3 by the -286 to get the 2.4?
Yeah.
Okay. Just
Yeah.
wanted to make sure.
Because this, let's see. Yeah, yeah. That times that divided by this gives that number.
Mhm.
And then this is that many moles of hydrogen. And this is kilojoules per mole, so the moles cancel and leave us with kilojoules.
Yeah.
Okay. I guess I went over a couple of minutes, but that leaves us just a little bit to finish off at 46. Let me make a note for myself. Pick it up again on Tuesday. This will be Friday's first. Second, third, fourth, fifth. 3, 5. Okay. That'll be part 2. And that should give us enough time to talk about the lab a little bit before we go in there. Of course, you're already going to have it in your notebook. Right?
Okay, stop share. And we're done for today.